My name is Finn Pond. I was a professor of biology at Whitworth University for 28 years and am recently retired. Amidst all that we have going on in the world to worry about, climate change is something worth uniting about for the future of our children and grandchildren and their children. Because affecting climate change is analogous to trying to stop a cruising oil tanker. Because of their huge mass, oil tankers take up to 3 kilometers in 15 minutes to slow and stop. To slow and stop the inertia of global warming will take decades and worldwide efforts. And unless we act quickly and intentionally, the consequences may be catastrophic. We need to act now, together, at this particular time in history. I'm here to give you the scientific evidence.
What I want to do is look at the evidence for a warming planet, that is, global warming is occurring. And then we'll look at the evidence for human activity in being responsible for that warming. And finally, we'll consider some consequences, many of which are irreversible and dire. As you can see, humankind is both the perpetrator and the victim of climate change. So let's begin with evidence for a warming planet. Here we're looking at a graph of surface temperature. It's over a year period, a seasonal cycle, beginning in 1880 and moving into the present. You can see here that the earlier dates, beginning in 1880, are color-coded in the blues and greens, and then we move to the oranges and reds. And you can see that each year, as we progress, we are becoming increasingly warm. You can see here, this is the state of the planet as of June 2020. Now, it may seem odd that we're doing an average. How do you do that, since there are seasonal variations and variations between the northern and the southern hemisphere? What is done is that temperatures are taken on a daily basis around the world at various stations, and those temperatures are compared to an average. The average is the temperature range, are temperatures from 1951 to 1980, a 30-year period. And any deviation from that average is marked on the graph. So you can see here that we have increasingly warmer deviations from those average temperatures over the decades. What we're seeing here is an animation of those temperature changes that are color-coded. Warmer temperatures are shown in the yellows, oranges, and reds. The cooler temperatures in blues. You can see that as we progress through the years and through the decades, we are seeing increasingly warmer temperatures. Since modern records began being recorded in 1880, 19 of the 20 warmest years have all occurred since 2001. The past 5 years have been the warmest of the last 140 years. We're seeing over that 30-year average from 1951 to 1980 an increase at present of nearly 1 degree Celsius, or 1.8 degrees Fahrenheit. 2019 was the second warmest year we've ever recorded after 2016, and it appears that 2020 will be even warmer than that. With all the warming surface temperatures, we're going to see ice melting. Here we're looking at the Arctic sea ice.
On September 18th, satellites observed that Arctic sea ice had reached its annual low. This year's sea ice minimum is effectively tied for the second lowest on record. And while sea ice grows and shrinks with the seasons, 2019 continues the downward trend of the extent.
The trends that we've been seeing with the sea ice minimum have just been a decrease. So in the 70s, since the modern record began tracking, to today, There's variation from year to year, but it's really just a downward trend.
Satellite observations show that Arctic sea ice is not only shrinking in extent, it is also becoming younger and thinner. That means less and less ice survives the annual melt.
The Arctic has actually warmed a lot more than the globe as a whole. There's something called Arctic amplification, which means that the temperatures in the Arctic have warmed about 2 to 3 times the global average.
A major cause of this warming is due to the loss of reflectivity, or albedo, of the sea ice. Snow-covered sea ice has a high albedo. This keeps the sun's energy from being absorbed by a dark ocean. But when sea ice begins to melt, it loses some of that reflectivity. And without the sea ice cover, the ocean will absorb most of the sun's energy. This creates a feedback loop that leads to more melting and warming in the Arctic.
We care about sea ice for a variety of reasons. One being because it does have an impact on things like our weather and our climate. Because of the albedo effect, if you decrease the amount of Arctic sea ice, you start warming up the Arctic. And when you start warming up the Arctic, you can start changing the circulation of the jet stream, which brings weather to us here in the mid-latitudes. The other reasons why we care about sea ice, Arctic sea ice in particular, is because we've seen such big changes due to warming, melting ice. It's a good visual to show that yes, the climate is changing, and it's because of warming.
NASA continues to monitor these changes to the Arctic so that we may get a better understanding of what we can expect in the future.
What we're seeing here is a graph showing the extent of the Arctic sea ice melt. There is, of course, an annual cycle. We build up sea ice during the winter months, and then that melts in the summer. And as you can see here, the melts are more and more extensive each year. This is where we are in 2020 as of July 25th. With the sea ice melting, we're going to see other changes as well. The Arctic is warming twice as fast as other parts of the planet, and this is going to have ramifications for global security, climatic changes in weather, commerce, and trade. As you can see here, the Arctic summer is leading to browning and dying off of the tundra itself.
Unprecedented warming and exceptionally low levels of sea ice are imposing dramatic, rapid, and disruptive change on marine ecosystems in the far north. The Bering Sea has been nearly ice-free for 2 winters in a row. The warmer water has caused marine species to move farther north, impacting vital commercial fisheries and indigenous subsistence harvests. There has been a cascade of impacts on the marine food web, from microscopic creatures to large marine mammals. Massive die-offs of seabirds and other animals were seen. This years-long pattern of climate warming and ice loss in the Arctic is likely to continue, threatening ecosystems and livelihoods with far-reaching global implications. The loss of ice, snow, and permafrost in the Arctic is causing damaging changes to the northern landscape. In 2019, the Greenland ice sheet continued melting at a dramatic rate. This will inevitably contribute to widespread coastal flooding in the years to come. Thawing of permafrost ecosystems in the Arctic is now releasing carbon to the atmosphere at a rate of up to 600 million metric tons per year, accelerating climate change. Changing growing conditions, including warmer summers, decreasing snow cover, and permafrost instability, lead to alterations in the vegetation of the Arctic landscape. This can strongly affect habitat for caribou, birds, and other wildlife, putting further pressure on northern ecosystems and communities. Indigenous communities along the Bering Sea are on the front lines of climate change. As sea ice disappears, so does hunting access to seals, whales, walrus, and other marine life.
There's less and less snow. and there's less and less ice. And that means trouble, not only us hunting and fishing, but the animals that we depend on.
We're seeing a lot of birds die off every summer. It's really gotten worse within the last 5 years. The lack of ice really hurts our food chain.
More open water exposes shorelines to storm surges, flooding, and increasing erosion. Despite the stresses of climate change, resilience is also a way of life for the region's indigenous peoples.
There's a lot to protect today before a total disaster happens.
Permafrost is defined as soil that is frozen for 2 or more consecutive years. Some areas of the Arctic have been frozen for well over 100,000 years. The permafrost may be a few feet thick or over 1,000 feet thick. And it's estimated that the permafrost of the Arctic may hold more than 1,500 gigatons of carbon. The carbon is released mostly as CO2, carbon dioxide, but may also be released as methane. Those carbon emissions from the permafrost are going to warm the planet, leading to more global warming, which will lead to more melting of the permafrost, creating a positive feedback. We also see ice on the ice sheets of Greenland and Antarctica melting. Greenland is losing ice 7 times faster than it did only 30 years ago. Here you see the surface mass balance for Greenland. If there is no net change in the amount of ice, we would be at 0. As you can see, we do get a buildup of ice and snow in the winter months, but then that's lost as we enter the summer. 2019, you can see we had a greater melting than ever before. Here we're looking at the extent of Greenland ice sheet melting in 2020. This is taken in August 2nd. You can see that some areas do build up increasing ice, but there's more areas that are losing ice. So the net change is a loss of the ice sheet. Here you can see the average, a 30-year average between 1981 and 2010. And you can see that in 2020, we are exceeding that average ice sheet melt. If we put 2020 in context of some other years, you can see that even though this year is higher than the average, it's not as great as what we saw in 2019, shown in green, or the 2012, shown in this orange color. So we do see that there is variation. Some years are going to be worse than others. But the fact that 2020 ice sheet melt was lower than the previous year does not mean that we've turned the corner on global warming. What we have to do is look at a long-term average. And there is a satellite program that's been monitoring the ice sheets, both in Greenland and Antarctica, since 2002. And what they've discovered is that there's a loss of about 280 gigatons of ice per year from Greenland. And this is causing a global sea level rise by a fraction of an inch, which may not seem like much, but we'll see later that that can be quite significant. So here's the data from these satellite observations. You can see that there is seasonal variation, but what's important is to note that the long-term trend is for a loss of the ice sheet. Here is it's represented graphically. You can see the color changes. The darker oranges and reds indicate greater amount of melting. Grace has also been monitoring the Antarctic ice sheet loss since 2002. And again, there's going to be natural fluctuations, but the long-term trend has been a steady decline in the amount of the ice. You can see we're losing it largely from the western side of the continent, from the peninsula, and this region here, which is Theiss Glacier. But we're also starting to lose it on the eastern side, which is significant. In Antarctica, we've monitored about 125 gigatons of ice lost per year, which will raise again the sea level by a fraction of an inch. We see that this year, in February, the temperatures in the Antarctic were about the same as in Los Angeles. And at the Antarctic Peninsula out here, we reached 65 degrees, the hottest ever recorded for Antarctica. What is happening here on the western side of the continent is that we have the Thwaites Glacier and Pine Island Glacier, which extend over the ocean, this West Antarctic ice sheet. We've been able to take robotic submarines and explore the underside of these ice sheets. And what we find is that there are warmer ocean currents moving in underneath the ice sheet. So we're getting melting from the underside. Also with the higher surface temperatures, we're getting melting from the top side. As that ice shelf thins, we get fragmentation, and we're breaking off large pieces of that ice shelf. You can see here that the grounding line, which is where the glacier contacts bedrock, has been receding. And so we get more and more of this glacial retreating. It used to be thought that the East Antarctic ice sheet was less threatened by climate change because it was thicker and temperatures tend to be cooler. But we're finding that the same thing is happening on the eastern side, as we saw with Thwaites Glacier. There's water moving in, warmer water, that is undercutting the ice sheet. What we're looking at here is Denman Glacier, which covers the lowest point on the Earth, 3,400 meters below sea level. You can see that the grounding line is receding. If this warmer water moves in and fills this basin, we could lose much of that ice sheet. And this could cause as much as a 5 feet sea level rise. Not only are we seeing sea ice melt and ice sheets melt, but we're seeing glaciers on mountains around the world disappearing. This is Grinnell Glacier in Glacier National Park from 1936, and this is what it looked like in 2014. We've gone from over 8 square miles of glacier with 150 glaciers active to only 25 active glaciers with nearly just about 1 square mile. Not only are we raising the surface temperatures on land, but the sea surface temperature is also rising. Here we're seeing a change in sea surface temperature. Again, the oranges and reds indicate warmer water. What you're seeing in this little box here is a portion of the Pacific Ocean which is affected by El Nino years. You can see it warms tremendously, which changes ocean currents, changes the animal life of the ocean. We're seeing here about a 2 degrees Celsius rise during these warmer El Nino years. And this leads to seasonal temperature extremes around the world. It leads to reduced sea ice and altered habitat ranges for both plants and animals. Here we're looking at the change in temperature at different depths in the ocean, from surface waters to mid-depth waters to the very lowest depths in the ocean, you can see that at all levels, temperatures are increasing. About 90% of the heat from global warming has been absorbed by the ocean, and this is because water has a very high heat capacity and can hold a lot of that heat that is generated by the greenhouse gases. What's significant is that the sea level rise is due largely to thermal expansion. We do have increased water entering the ocean through melting glaciers, through draining of watersheds, through Antarctic melt from melting Greenland, but much of it is from thermal expansion. As the water warms, even a small amount, it expands. And this increased volume is what's responsible for about half of the sea level rise over the past 140 years. Here we see tidal gauge measurements from 1880 to the present. And we also see some satellite recordings of sea level change. What you can note here is that in that 100-year and 40-year period, we've seen about an 8-inch rise in the oceans. Now, this is not going to be uniformly seen around the world because topography along the coastlines can have an effect, but the sea levels are rising. And they're rising at a faster rate. So you can see that there is significant evidence that we are in fact warming. The question then is, what is responsible for that global warming? Is it in fact human activity? Well, we know that climate changes throughout history, and there are ways to monitor what the temperatures were in the past. We use proxy data to reconstruct those climatic conditions. We can use tree rings, for example. Looking at the width and the density, we can calibrate those differences in the tree rings to temperatures at the time in which those rings were formed. A note here, we're also looking at isotopic composition. Certain isotopes are accumulate more readily in organic matter. Oxygen 18, for example, has a different ratio to oxygen 16. Using that, we can calibrate the temperatures at the time that the rings were forming. Another way we can monitor past temperatures is looking at fossil pollen. Plants produce a particular kind of pollen that's identical or can be identified to a particular plant, which is known to grow under particular conditions. So we can get a picture of what the climates were of the past. We can also look at corals, oxygen isotopes, and trace metals can be calibrated to water temperature. So an analysis of coral can tell us what the temperatures were at the time that coral was formed. We can also look at microfossils and various chemicals in the ocean sediments and calibrate that to different temperatures of the past. One of the best proxy data is ice cores. Ice cores can be dated because there are seasonal banding patterns at the time of deposition. So we can go back in time. And there are gases trapped in the ice cores. The gases trapped in the ice can tell us both the composition of CO2 in the atmosphere. It can also tell us what kind of isotopes were present at the time of deposition. And again, looking at hydrogen and oxygen isotopes, we can determine the temperature in the past, because the deposition of those isotopes will vary depending upon the temperature at the time they're deposited. So what we're seeing here is temperature anomalies during historic periods, going back a couple thousand years. There are a number of studies represented in this diagram. Each of these use different kinds of proxy data. Some are only looking at land areas in certain locations, Northern Hemisphere, for example. Some are looking at data from the water. They're all using different proxy data sets. We can see that there is natural fluctuation. But when we move into the more recent times, in the last several hundred years, we see there is a dramatic change that we can all agree on. With Antarctic ice cores, we can go back 800,000 years, and you see again, there is a natural fluctuation. Again, we can monitor the temperature at the time that the ice core, or the banding patterns of the ice core were formed because of isotopic concentrations. So the question is, if there is natural fluctuation and variations, how do we know that what's happening now is not simply a natural fluctuation? As you can see, there's been a recent warming period. Might that simply explain what we're observing? Well, there's reasons that we see those fluctuations over long periods. It has to do with variations in the orbital cycle of the Earth. Here you see eccentricity of our orbit. Our orbit does change. This is, of course, greatly exaggerated. But when Jupiter and Saturn are aligned in a particular way, the gravitational pull that they exert will change the orbital pattern of the Earth. And that brings the Earth into a closer proximity to the sun, which means there's more solar irradiation. That changes the temperature. We can predict when those alignments are going to occur and predict that on a 100,000 year cycle, we're going to see these warming trends. Also, there's axial tilt. The axis of the Earth is known to fluctuate, to change, and that's on a 41,000 year cycle. Finally, there's a wobble or a precession in our rotation around the axis, and that is predicted to occur in a 23,000 year cycle. All these different factors affecting orbital cycles will affect the temperature of the planet. And so we go through those natural fluctuations. Here we're looking at historic records of solar irradiance, how much sunlight is hitting the planet. There's an 11-year sunspot cycle that affects the solar irradiance, the amount of heat that the planet is receiving from the sun. Here we're looking at the actual recorded data of temperature change. And what you can see quite clearly is that the amount of solar irradiance does not explain this recent increase in global temperatures. And in fact, the only way we can explain this increase is by introducing the effect of greenhouse gas emissions. Here from the year 2000 was a study that looked at how well we can predict the temperature fluctuations. So we have in black here the observations of temperature changes taking place. And here is a model that only accounts for solar activity, volcanic activity. So it's the natural fluctuation that would be expected in temperature. Only when we add greenhouse gas emissions and the sulfates. By the way, sulfates will lower the warming effect of the greenhouse gases. But only when we add these human-generated gases to the atmosphere can we explain the observed temperature changes. What happens in the greenhouse effect is that radiation from the sun is absorbed by the Earth's surface. Some, of course, is simply reflected, but the heat that is absorbed by the Earth's surface will be re-radiated back out towards the atmosphere or towards space, but much of it will be trapped in the atmosphere by those greenhouse gases, re-radiated back to the surface, warming the planet itself. Now, without those naturally occurring greenhouse gases, which include water, carbon dioxide, and methane, the planet would not be quite as hospitable. It would be, the average temperatures would be closer to 0 degrees Fahrenheit instead of 59 degrees Fahrenheit. Now, I should point out here that water is a major greenhouse gas. It traps heat, but it's not important in considering the effects of the global warming that we're observing now. The reason for that is that there's a limited amount of how much water vapor can be held into the atmosphere, and that's dependent upon temperature itself. So the water vapor is not controlling the temperature, but rather the reverse. The temperature is controlling the water vapor. So there's a limit in how much water vapor can be in the atmosphere, and that sets a limit on the extent to which water is responsible for the greenhouse effect. CO2 and methane do not have such a limit and can increase continually, and that is what we're seeing. So these are the gases responsible for the global warming we're observing. Both carbon dioxide and methane have some natural sources. Nitrous oxide and fluorinated hydrocarbons are primarily the result of industrial processes. They are significant, but it's the CO2 that is most dominant in the causing the global warming. In this diagram, what we're seeing here are CO2 equivalents in the atmosphere, and I'll explain that here in a bit. So we can compare these different greenhouse gases by looking at their global warming potential, by comparing them to CO2. Notice here that these gases have different life expectancies in the atmosphere. The variability of CO2 depends upon particular locations on the planet, climate patterns, and so on. But CO2 can last for hundreds, even up to 500 years in the atmosphere. Methane will only stay in the atmosphere for about 12 and a half years, but it's much more potent as a greenhouse gas. Over a 20-year period, methane has an 86-time greater effect on warming than does CO2, which means that 1 ton of methane is equivalent to 86 tons of CO2 in the atmosphere over a 20-year period. Because it has a lower life expectancy in the atmosphere, over a 100-year period, that decreases to only about a 28 times greater effect. Notice here that nitrous oxide has a much stronger warming effect, as does the hydrofluorocarbons, which are used in refrigeration in industrial systems. And for this reason, for their great potential, European countries have now moved to ban particular kinds of hydrofluorocarbons. But methane is both a human-generated product, but also a natural product. You can see here it's doubled in recent years, which is quite significant and concerning because of its stronger global warming potential. We've known for a long time that methane is released from the ocean floor. Here you can see as bacterial metabolism degrade plant and animal material that settles to the bottom of the ocean, we see methane gas bubbles being released. We've known that for some time, but what is particularly concerning now is that we're seeing the same process now occur in Antarctic waters, which previously had thought to be too cold to generate that same kind of metabolism.
This year, NASA released a new visualization modeling the sources and transport of methane across our globe. With this new visualization, we can see how methane sources vary by location and season. In South America, the Amazon River basin and its adjacent wetlands flood seasonally. This creates an oxygen-deprived environment that is a significant source of methane. In the last 200 years, methane concentrations have more than doubled, mainly due to human activities. Europe is the only region to show a decrease in methane emissions over the last 20 years. In India and Southeast Asia, rice cultivation and livestock are two of the driving sources of methane. In China, economic expansion is driving a high demand for fossil fuels, resulting in an increase in methane emissions. This is a stark difference to the Arctic, where natural sources, such as natural wetlands and potentially thawing permafrost, account for more than 70% of the region's methane emissions. Taking a step back, we could see that methane has vastly different sources around the globe. By getting a better sense of the story of methane, scientists and policymakers can better understand the sources of methane emissions and work to reduce this greenhouse gas.
Let's go back to the Antarctic ice core data. Shown here in light blue are the temperature fluctuations, which we saw earlier. These are natural fluctuations in temperature, but note also that we can see that CO2 parallels those changes. In fact, CO2 and temperature are tied to one another. When we look at more recent data, we here compare the ice core data, those fluctuations in CO2, to what we have at the current level. Notice here that only rarely did those natural fluctuations move above this 1950 level of about 300 parts per million CO2. We're now well over 400 parts per million CO2. The CO2 is monitored daily at the Mauna Loa Observatory in Hawaii. There is a natural seasonal fluctuation in the amount of CO2. This has to do with temperature and vegetative activity. The highest levels tend to peak in late spring, in May, for example, here. And in May, we reached 417 parts per million, which was a 2.4 part per million increase over last year. The CO2, as you might expect, is coming from burning of fossil fuels, either in transportation or in coal-fired electric generator plants, in various forms of industry. There's commercial and residential usage in agriculture. This is the pattern for the United States. As you can see, global greenhouse gas emission is somewhat different because different levels of industrialization, but still, it's the burning of fossil fuel through heat production, agriculture, forestry, transportation, and industry that are primarily responsible. Last year, China contributed 28% of the greenhouse gas emissions, whereas the United States had only 14%. What we need to remember is that in the United States, on a per capita basis, we far exceed what is produced in other countries. Cumulative, the United States has been responsible for putting CO2 in the atmosphere over a longer period of time than China, for example, and is responsible for 25% of the CO2 that is now present in the atmosphere. So we've seen that there is evidence that the planet is warming, and there is evidence that we are responsible. Our human activities are causing the rise in greenhouse gases, which is causing the global warming. So let's look now at some of the consequences. First of all, we're going to see more natural disasters. Storms, floods, and droughts, altered farming conditions. There's going to be variation on the planet. Some areas will have colder winters, some will have hotter, drier summers. But overall, the planet is warming on average. That additional heat put into the atmosphere and into the oceans intensifies the storms that we're experiencing. The larger and more frequent hurricanes. It's changing weather patterns, which brings the droughts, which lead to more damaging fires. Overall, we'll see in this next century a lack of food security and food shortage, less clean water, increased diseases. It's predicted we're going to see more emerging diseases, things coming from animal sources into the human population, such as the coronavirus that we're experiencing now, economic instability, and social disruptions. These changes are going to affect people around the world, but it's going to be much more severe in certain areas of the world, especially on the African continent. So let's look at what the prospects are. If nothing is done at all, if we do not have any policies to abate greenhouse gas emissions, we're looking at a nearly 4.8 degrees Celsius increase in temperatures by the year 2100. This is over an 8.5 degree Fahrenheit change. This is going to be quite catastrophic. The Paris Climate Agreement wants to limit the temperature change by the year 2100 to only 1.5 degrees Celsius. Currently, you recall that we're just below 1 degree Celsius above the 1951 to 1980 average. If we can't achieve this, the Paris Climate Agreement said let's at least keep it below 2 degrees. Well, at present, if we're able to meet the pledges and targets that various countries have agreed to, we might be just slightly below the 2.0, but that's unlikely. Optimistically, at best, we're looking at a 2.8 degree Celsius change. Under current policy, and this is assuming that we have new regulations and new developments in energy technologies, the current policies that are in place around the world predict that we're looking at about a 3.2 degrees Celsius change. So what does that mean? Well, it means that some countries need to, that are most responsible for the releasing of the greenhouse gases are also the ones that are least active in trying to reduce those greenhouse gases. Notice here that the United States is releasing greenhouse gas emissions into the atmosphere at a rate that is pushing towards the greater than 4 degrees Celsius change. So why is it important to take action now? Well, first of all, we're on track for that 3.2 degrees Celsius change by 2100, and there's going to be a time lag between what we do and when we feel it. Greenhouse gases linger in the atmosphere for hundreds of years. So even if we stopped emitting greenhouse gases today, global warming will continue for at least several more decades, if not centuries. So it's important that we act now. Now we still have a chance to limit global temperatures to that 1.5 degrees Celsius that was listed in the Paris Climate Accord, but it requires immediate and concerted efforts. To limit warming to 1.5 degrees Celsius by the year 2100, we would need to reduce the gigatons of CO2 equivalents, that's the equivalence of CO2 with methane and nitrous oxide included, from about 50 gigatons now to 25 gigatons by 2030. We need to reduce it by half. And to be at zero level by mid-century. If in 2010 we had all agreed to reduce carbon emissions by 3.3%, we could reach that 2030 goal. Now in the year 2020, because we have not been able to reduce carbon emissions, we would need to reduce it by 7.6% annually to reach that 2030 goal. Interestingly, this year with the pandemic and reduction in carbon dioxide emissions because of a decrease in transportation activities and so on, we came close to reaching this level. But if we don't act now, if we wait 5 years, then it's going to require a 15.4% annual decrease in order to reach that goal, which is nearly impossible. So every fraction of additional warming beyond that 1.5 degrees Celsius is going to result in increasingly severe and expensive impacts. So let's take a look at some of those. If we hold climate change to a 1.5 degrees Celsius warming by the year 2100, we're still going to affect a great proportion of the human population. Extreme heat is going to affect nearly 4 billion individuals in that time. Water stress, nearly 3.25 billion people. We're going to see millions of individuals affected in terms of power production, crop yields, habitat degradation, and so on. With only a 0.5 degree increase to a 2 degrees Celsius warming, again, there's going to be drastic effects. Up to 6 billion individuals affected by extreme heat, 3 2/3 billion of people affected by water stress, and so on. Now, I should point out that population projections are that we will exceed 8 billion people before mid-century, and will be around 9 billion people before the end of the century. Currently, we're at about 7.4 billion people. We're on track for a 3.2 degrees Celsius change by the end of the century. With another 0.5 degree warming, we're going to affect nearly 8 billion people with extreme heat, with water stress, and so on. Right now, water-related events are estimated to displace 143 million people by the year 2050. Rising sea levels are already affecting a number of populations around the world along coastal areas, and also in tropical Pacific islands. It's estimated that sea level rise could cost the global economy $14 trillion in loss or damaged assets by the end of the century, and that we're going to see an increase in climate refugees, people being exposed to episodic coastal flooding and having to flee those areas. We'll see more than 1 million square kilometers of coastline affected. This is an area about twice the size of France. The National Climate Assessment in 2018 concluded that the number of heat waves, heavy downpours, major hurricanes had increased in the United States, and the intensities of these events also increased. In 2016, a study of such extreme weather events indicated that most of these were, if not caused by global warming, were exacerbated by global warming. So we had extensive drought, excessive heat, fire, arid conditions, and so on. So again, global warming has been implicated in the extent and intensity of these extreme weather events. The weather events that we're experiencing are costing more and more. The number of billion-dollar weather disasters is expected to rise over the next several decades. And especially along the western states, from Alaska down to Mexico, we're seeing increased fires and more intense fires. This has to do in part because of the climate change. The warmer, drier conditions are drying out the vegetation, creating higher winds, which fuel these fires that we're experiencing. The US is not going to escape these extreme heat waves. It's projected that we're going to see a number of dangerous days in terms of the heat index by mid-century. So you can see here by 2050, we're expected to experience 178 extreme heat and humidity conditions in Miami, 161 in Phoenix. Because of the humidity on the eastern states, they're going to be affected more severely. Global warming also threatens human health. Climate change is going to alter the distribution of insect vectors, so we're going to see increases in vector-borne diseases such as Lyme disease, dengue fever, West Nile virus, and so on. We're expecting subtropical diseases such as malaria to increase by as much as 33%. Lyme disease, for example, in the United States has been expanding, or the range of Lyme disease and the number of incidents has been expanding in recent years. You can see here with the range at which individuals are subject to Lyme disease has been increasing. Not only that, but we're seeing that allergy seasons are becoming longer, up to a month longer, up to 27 days in some locations. In a study that was done with ragweed pollen, and ragweed was grown in laboratory under different CO2 conditions, and they found that with increasing atmospheric CO2, shown here, we have an increased number or increased amount of ragweed pollen production, shown here in the blue. Pollen counts of all varieties are expected to double in some parts of the country by 2100. So here's our current tree habitation. By 2100, we're going to see a different distribution of trees. That's going to change the various kinds of pollens. This is under a low emission scenario. This is under a high emission scenario if nothing is done. Much of the country is going to be affected. Climate change can also increase the spread of cholera by creating different patterns of rainfall to favor the disease's transmission. So human health is going to be impacted in a number of ways. As we increase CO2 level, we can see rising temperatures, more extreme weather, rising sea levels. These are going to cause a number of changes: water quality, environmental degradation, extreme heat, and so on. And that's going to have an effect on human health. Biodiversity is also affected, and this study, which was done in 2003, illustrates that for several decades now, organisms have been affected by changing weather patterns, warming planet. In an evaluation of over 1,700 species, they found that half of them had been affected by climate change. The habitats had changed. They were moving to higher elevations or moving poleward into cooler climates. Breeding was affected. Reproductive cycles and patterns were affected as the temperatures of their habitat warmed. Ecosystems are affected in a variety of ways. Here we're looking at climate change in terms of change in precipitation, temperature, extreme weather events. That's going to have an impact on various species and populations. Also, those changes are going to affect the physical environment, permafrost thawing, soil drying, reduced snow cover, and so on. That's going to affect the ecosystems as well as the biodiversity. We're going to see a change in distribution. Organisms are going to relocate, and communities are going to restructure as best they can in different regions of the continents. We're going to see a change in the physiology. We're going to see different growing patterns. We're going to see reproductive changes as the timing of reproduction is affected by temperature. And we're going to see a change in quantity. There's going to be a shift in the size of populations and amount of biomass cover and so on. And this is going to affect ecosystems around the planet. Many species are already at risk for extinction. 1 in 6 species now is threatened by climate change. Notice here that if we reach that 3.2 Celsius change by year 2100, we're going to have a much higher rate of extinction. There's also going to be social and political consequences from climate change. Mass displacement due to flooding and loss of access to adequate food and water resources. We're going to see climate refugees. And already refugees moving across borders are creating a lot of social and political problems in the world. So we can expect that we're going to see increased hostilities and violence as different ethnicities, religious and cultural beliefs come into contact as a result of these mass displacements. So I want to give you a quote from earlier this year from the National Security Military Intelligence Panel. Even in scenarios of low warming, each region of the world will face severe risks to national and global security in the next 3 decades. Higher levels of warming will pose catastrophic and likely irreversible global security risks over the course of the 21st century. So how much time is left?
Scientists point out that women and children will be the worst hit by climate change, despite this view that they are
And we fool ourselves if we think we can fool nature, because nature always strikes back.
The eyes of all future generations are upon you. And if you choose to fail us, I say we will never forgive you.
I'll close with this quote. We are the last generation that can prevent irreparable damage to our planet. Climate justice is intergenerational justice. When we first come to realize that our actions are harming another individual, we have at that point a moral obligation to change our behavior to the extent that we now understand the detrimental effects of human activities on the health and sustainability of the environment. We have a moral obligation to behave differently, to rethink the ways in which we live. Thank you.